All right, class. Welcome to what is it? Statistics 101 Data Analysis in Quantitative Research. Data analysis is an essential process of transforming raw data into meaningful insights. Without analysis, collected data is merely an uninterpreted collection of numbers. In quantitative research, raw numerical data is made meaningful through statistical procedures, which are often presented as comprehensible tables, charts, and graphs. So, before we do anything with our data, the first step is always the data preparation process. First of all, we code our data, which we learned in our previous weeks on how we can do that. So, data coding, qualitative to numerical conversion. For example, we can do gender can be coded where female is assigned 1 and male is assigned 2. Researchers prepare a coding sheet that dictates how particular numbers are assigned to each variable. They keep like a sort of dictionary to not confuse anything. Now, there's a strong rule. The number 0 should not be defined as a numerical value during this process. Or when you do anything that involves any sort of math, everything breaks down, so you don't use 0 in normal context. Or maybe the reason is that it's probably not a ratio scale research, so that might be also a reason, but I'm not sure. But don't use 0. So the second one is data entry. You put the data that you've prepared into a program like Excel, like SPSS. It's easy to understand. So each row here represents another participant. Here we have an example. Each column is a specific variable. Variable 1, gender. Variable 2, age. Variable 3, income. I take it that you know how to read a table, but just in case you don't, this is how it looks. These are the data for participant ID 001. So they are, what is it? Female. They are aged 25 and they make 45K a year. Now we have data cleaning, which ensures accuracy before analysis by checking for repeated errors, missing values, or duplicate entries. For example, you may get an age being entered as 222. Now, that's quite unrealistic. If someone was 222, they would probably be my grandfather. Data cleaning also allows for modifying data, such as regrouping income brackets or merging variable categories. What does merging variable categories mean? For example, you have data like a bunch of incomes 45,000, 52,000, 48,000. You may group this data into middle class, just as an example. So, the use of statistics. We have descriptive statistics and inferential statistics. The main difference between descriptive statistics and inferential statistics is that descriptive statistics simply summarize the data that you currently have. What does this data mean for us? How does our data look? You provide the analysis and you try to make up stuff based on that data. But inferential statistics guess the future. According to this data, they try to generalize this data. They try to generalize the findings from this data. So, the way you actually understand what you can do with this data is descriptive statistics, where if you actually put your mind into it and try to figure out what this data means for the real world, for the practical sense, that's inferential statistics. You test hypotheses and draw inferences. We have 1, 2, 3, 4, 5, 6, 7, 8 terms to learn here. Now, first of all, we're going to learn about frequency distribution. You're going to get a bunch of data. You're going to get a bunch of participants. You're going to get a bunch of values that the participants answered for a given set of questions. And you need to plot them somehow. You need to visualize them. So, what you do is you create a frequency distribution. So, from this example, we can see that this person or this value has been answered like 3 times, maybe. Let's call this 1 through 5, or how many? Yes, 1 through 5. Let's say this is a chart for happiness. We can say that 2 people answered that they are very unhappy. And then 3 people said that they are moderately happy. And I guess 6 or 8 people said that they are happy. And then 3 people, or about, I guess 4. 4 people said, man, I guess I'm happy. Or they are maybe happier than the ones previously. God damn, I cannot interpret graphs. But the thing is, as this bar goes up, this is the frequency, this is the actual data. I don't know if you need to know these, but I know statistics, so I just want to blurt some stuff. So these guys are very happy, is what I'm saying, but they are a minority. So we have multiple ways of organizing data. It goes nominal, ordinal, and interval data. Nominal means, I think it is either, it should be numbers, like 1 to 5. Ordinal, no, maybe nominal is a categorization. I'm really not sure. I will probably update these here to integrate them better. But simply just know that nominal, ordinal, and interval data can be used. One of them stands for classes, like female, male. One of them stands for ranks or orders, like first place, second place, level of education, like high school, university, etc. Interval just goes 1 to 5 with a fixed interval ratio, etc. I don't know if you need to know these. So another thing that we are introduced to is the Cronbach's alpha coefficient. Now, the only thing they say about this is that 0.60 and 0.80 between these two numbers is considered as good reliability data. But if you go even higher, from 80 to 100, it means that you are in a perfect position. Your data is very reliable. And then we have the measures of central tendency. Mode is the most frequently appearing value. What does this mean? In the dataset 5, 6, 2, 4, 5, 4, 7, the modes are 4 and 5. Why is that? 5 occurs 2 times, 4 occurs 2 times. Whereas the other values, 6, 2, and 7, only occur once. If there was a third 5 here, then the mode would be 5 instead of 5 and 4. Median is the exact middle value of an ordered dataset. The fact that it's ordered is very important. You need to order it from lowest to highest. And if the value that lands in the exact middle is the median. If there are 2 values like this, for example, then it would be, the median would be 5.5. Just extra information, cherry on top. Arithmetic mean is what you get when you sum up all of the numbers in the dataset and then divide by the amount of samples you have. But it is extremely sensitive to extreme outliers. So just to think of an example, when you have a village full of people getting 100 lira, 120 lira, maybe 140 lira. This is just not even K, dude. It's just 160. And then Elon Musk lives there with his 100 billion trillion dollars. What happens? The average income for this village becomes something like this. I don't know, I haven't calculated it, but it's extremely sensitive to extreme outliers. Whereas if we took the median would be this. You see why it is considered the most sensitive. We also have measures of dispersion, how varied your data is. Variance indicates how far values deviate from the mean. A lower variance means the data is clustered and close to the average because they are not far away from the mean. They're not as spread out. And a higher variance means the data is spread out. It's more varied. Your data is more varied. It's not close to the mean. I don't know if you can understand this without getting into a statistics class, but I hope you can. A standard deviation is just the square root of the variance, and it's just a human readable way of the variance. It's not really different from variance. It's just something we can interpret as humans, because variance might be something like 620, whereas the standard deviation being like, I don't know, 5. The z-score is a standard score indicating how far a given value is from the mean, measured in units of standard deviation. So you assign 0 as the mean, and how far away a value is in standard deviation units is z-score. I don't know if I was able to explain it, but if I draw something like this, I don't know if I will be able to. This will be your 0 point, this will be your z1, this will be your z2, and the distance between these guys will be a standard deviation long, just like a ruler. There will be raw values here, and these will be your z-scores. I don't know if you need to know these, but I just know them, so I want to do something with them. Inferential statistics go beyond description, as we discussed. We have multivariate statistical analyses. Now we have 1, 2, 3, 4, 5, 6 types of analyses with a duplicate here, which is perfect, just to get it in your mind. So the first one we have is the correlation analysis. It determines the strength and direction of a relationship between variables. The correlation coefficient ranges from -1, which is a strong negative relationship, to +1, which is a strong positive relationship, with 0 being weak or no correlation at all. So you are trying to see if two things move together or move opposite of each other. So if you have a coefficient of 0.50, for example, this means the data is kind of affected by each other, like moderately affected by each other in a positive manner. What can we give an example to? Like treating your partner in a good way has a positive correlation coefficient with your partner being happy. Whereas treating your partner like shit and them having a bad day or hating you also has a positive correlation. It just tries to show if the variables move together or against each other, or if they are not affected by each other at all. Okay, perfect. Analysis of variance. We call this ANOVA. It tests for significant differences, usually probability of less than 5%, among 3 or more groups. Normally, for 2 groups of data, we use a t-test. But if it's more than 3 groups, or just 3 groups, if it's more than 2 groups, we use an ANOVA. Testing if 3 or more different groups have different average results or not. For example, test scores across 3 different schools. Is this school performing better than the others or not? Regression analysis demonstrates how independent variables like age or education explain changes in a dependent variable. You are trying to predict the future. It shows how much your cause variables, like age or schooling, actually change your effect variable, like happiness, or what we described, like treating your partner like shit and your chances of breaking up. So you can only say that there's a correlation between them, but you cannot tell if there is an actual cause and effect relationship between them with a correlation analysis. So you have to do a regression analysis to actually see that cause and effect. So another example to correlation is in the summertime, as ice cream sales go up, or as more people eat ice cream, the cases of drowning also go up. So we can say that they have a strong correlation, but people dying does not necessarily mean that they will eat more ice cream. So this must mean that there's either a mediator variable or something else. This is what we use. This regression analysis is what we use to actually see if there's a cause and effect. A discriminant analysis is used when a dependent variable is categorical. So you are trying to discriminate things. To give a very offensive explanation or an example, which will help you understand probably, is discrimination by race. You can put people with more melanin in their skin to the black people category, where you can put people with less melanin in their blood, or no, less melanin in their skin to the white people category. You have predetermined groups that you are trying to discriminate people into. Does it make sense? For me, it does. I hope it does for you. There is also cluster analysis, which is when you don't have predefined groups. So an exploratory method that groups similar individuals or variables into clusters that were not predetermined. So you don't know anything about your data set. So you let the program run and you try to see if that program can find any similarities between data sets. Like, do these data move together? Or is there a correlation between them? Or something like that. It creates clusters for you. And in the end result, it tells you, okay, so I've grouped these variables together, like these three variables or these three values are very strongly linked with each other because I saw them going up with together, and I believe these can be a cluster. So things that are linked but are automatically occurring. And the program gives you, what is it, cluster 1, cluster 2, cluster 3, and then you name them into whatever you deem fit. Let me see if there's anything else. Brand new categories you hadn't thought of yet. Yes. Factor analysis aims to combine a large number of variables into a smaller set of common factors, simmering down a giant messy list of questions or variables into a few core big picture themes, like taking a 50 questionnaire items about feelings and boiling down to just anxiety or excitement. There is two things that need to be taken into account. The first of all is adequate sample sizes. So you have to have big sample sizes or adequate sample sizes. And you need to perform your correlation checks. They must have meaningful correlation between them, which is checked using KMO and Bartlett's tests. I don't know how these work. I've tried to understand, but they are too advanced for me, so I doubt the teacher will ask anything about that in the exam. It also uses techniques like Varimax rotation to make data more interpretable and groups factors with an eigenvalue greater than 1. It feels like I'm reading a spell book from Harry Potter. So an eigenvalue greater than 1, I don't know, I guess it means that these factors can be grouped and are correlated with each other. And a varimac rotation means it kind of spins the data around for looking from a new perspective. When you think of it in a 3D space, it kind of makes the data align with each other and makes the data actually choose a side instead of kind of hanging around in the middle. In short, looking at these 8 again, correlation analysis asks whether or not two variables have any relations with each other. Analysis of variance looks at if there is a significant difference between 3 or more groups. Regression analysis tries to find out if your independence variables actually affect your dependent variable. Discriminant analysis tries to put dependent variables into categories, like based on characteristics, but the categories are already existing. Cluster analysis, the same thing, but when you don't have predefined categories. Factor analysis tries to combine a large number of variables into a smaller set of common factors. And then, lastly, we have 4 additional statistical tests. The first one is chi-square test. It determines if there's a significant relationship between 2 categorical variables by comparing expected and observed frequencies. So you have an expected amount of results from for the answers that people give to these categorical variables. And if the expected answers are given, I guess they are grouped together, or they are trying to check to see the difference between them. I'm not really sure, but it seems to be similar to the approach that we talked about here. The ideal types thing, where you compare reality to a model. I'm not sure though. So if you see, but the keyword is 2 categorical variables and a significant relationship between them. If you see 2 categorical variables, it's a chi-square test. A t-test is a parametric test used to find statistically significant differences between the means of 2 independent groups, assuming the data has a normal distribution. Now, a normal distribution is basically this chart you see here, the bell curve, as you might have heard it before. When the data is a normal distribution, you can do tests like z-scores, t-scores, etc. But when the data is not normal, so non-parametric, you have to resort to 2 other tests. If your data has 2 groups and you want to compare them, you look at the U-test, because it's got a split end, you see? U. It's 2 groups, 1 and 2 groups. Yeah, Mann-Whitney U-test. But if you have 3 or more groups, then you look at the H-test. You see it has 4 forks, H4. And it's basically the non-parametric counterpart to ANOVA. It's the same thing. And the U-test is also the same thing as the t-test. I guess I didn't explain t-test too much, but because I don't really know if I can explain it that well, but it basically tries to see if there's a statistically significant difference between 2 samples. You get 1 sample, and your average from 1 sample is like 50. You get a class of 10 people, and they get an average of 50 grade. And then you take a second class, you inject them with cocaine, and then you try to see if their average score changes. If it goes to 80%, then you say, yes, this is a statistical significant score. If their standard deviation is 10, and then it becomes a t-score of 3, which is highly highly statistically significant. Don't let me bore you. If you want to learn more, you can check out my statistics lectures, I guess, or summaries. But yeah, that's it.